हेलो एंड वेलकम ऑल ऑफ यू। मटेरियल साइंस में सबसे पहले हम लोग पढ़ेंगे क्रिस्टलोग्राफी के बारे में। सो व्हाट इज क्रिस्टलोग्राफी? क्रिस्टलोग्राफी इज अ ब्रांच ऑफ साइंस इन विच वी स्टडी द इंटरनल स्ट्रक्चर ऑफ क्रिस्टल्स, its properties and symmetricity in its internal and external structure. In this chapter we will study about unit cells, space lattice, lattice points, Miller indices, atomic packing factor and crystal defects. Lattice points are the positions or coordinates where we can place an atom, so we can find either an atom or vacancies at the lattice points. Unit cell is the smallest part of a crystal. The whole crystal structure can be formed by the repetition of these unit cells. A primitive unit cell is the cell that contains one lattice point only. And if all the atoms at different lattice points are identical, then the unit cell is called Bravais lattice. When you arrange lattice points in a three-dimensional space, then you can find there are only 14 independent ways of arranging points in 3D space. These 14 Bravais lattices belong to 7 crystal systems, which we are going to talk about next. The first one is called cubic crystal system. Here all the edges of unit cells are equal and angle between any two sides are equal to 90 degree. Here we are assuming A, B and C are the three different edges of unit cell, and alpha, beta and gamma are the angles between two edges. That is, alpha is angle between B and C, beta is angle between A and C, and gamma is the angle between A and B. This crystal system can have three different space lattice. The first one is simple cubic, where atoms are placed at 8 corners. The second one is body-centered cubic, in which atoms are kept at 8 corners and also at body center of the unit cell. And the third one is face-centered, in which atoms are kept at 8 corners and at the 6 face centers of the unit cell. The second crystal system is called tetragonal. Here A and B are equal, but C has different length. Alpha, beta and gamma angles are all equal to 90 degree in a tetragonal space lattice. Tetragonal structure can have two different space lattices, that is simple cubic and body-centered cubic. The third crystal system is orthorhombic, where none of the side pairs are equal, but alpha, beta and gamma angles are all equal to 90 degree. It can have three possible space lattices, that is simple cubic, end-centered cubic, where lattice points are at 8 corners and at 2 face centers opposite to each other. And also it can have body-centered lattice. The fourth one is rhombohedral, where A, B, C are all equal. Also alpha, beta and gamma are equal but not equal to 90 degree. It can have only simple cubic lattice structure. The next one is hexagonal, where A equal to B but not equal to C, and alpha equal to beta equal to 90 degree, whereas gamma angle equal to 120 degree. The only possible lattice is simple cubic, in which lattice points are at 8 corners of unit cell or at the 12 corners of the hexagonal prism and at center of two hexagonal faces. The next one is monoclinic, where A, B and C all have different lengths and alpha and gamma angles are equal to 90 degree but not equal to beta. Monoclinic structure can have simple cubic and end-centered lattice structure. The last one is triclinic. In triclinic, none of the A, B and C are equal to one another, and also all the angles alpha, beta and gamma have different values and none of them is equal to 90 degree. Triclinic crystal system can be arranged in simple cubic lattice structure. Now let's see different cubic crystal structures. There are 4 cubic crystal structures where atoms are at the 8 corners of the unit cell. Body-centered cubic, where atoms are at the corners of the unit cell and 1 atom at the body center of unit cell. Face-centered cubic, in which atoms are placed at 6 face centers of the unit cell and also at 8 corners of the unit cell. And the diamond cubic crystal structure, which consists of 2 interpenetrating FCC arrangement of atoms. Now let's study about the atomic radii and packing efficiency of the crystal structures one by one. Let's start with simple cubic. In this crystal structure, we can easily deduce that the edge length of the crystal is 2 times the radius of the atoms. So A equal to 2R and atomic radius R equal to A by 2. Now atomic packing factor or packing efficiency is defined as the total volume occupied by the atoms in a unit cell divided by the volume of unit cell. Total volume occupied by atoms can be calculated by multiplying volume of one sphere to the effective number of spherical atoms in a unit cell. Here n equal to effective number of atoms in a unit cell. Since only 1/8 portion of an atom is inside the unit cell, so n equal to 1 by 8 into 8 atoms equal to 1 atom. So now after putting R equal to A by 2 and n equal to 1, we get atomic packing factor as 52.4%. Now let's calculate packing efficiency of a body-centered structure. There is an atom at the body center of the unit cell. If we draw a body diagonal in the unit cell, we can easily see that it is equal to 4 times the radius of the sphere. So here 4R equal to root 3 times A. So R equal to A root 3 by 4. In BCC there is one extra atom at center, so effective number of atom would be 2 here. So after putting n equal to 2 and R equal to A root 3 by 4, we will get atomic packing factor equal to 68%. Similarly, we can calculate packing efficiency of face-centered cubic structure. Here we can see the face diagonal, that is root 2 times of A is 4 times the radius of a sphere. So 4R equal to A root 2 and atomic radius R equal to A root 2 by 4. Here effective number of atoms inside a unit cell equal to 4, that is 8 into 1 by 8 equal to 1 at corners and half into 6 equal to 3 at face centers. So putting all the values, we will get atomic packing factor equal to 74% for FCC. And at last, in diamond cubic structure, which is formed by 2 interpenetrating FCC arrangement, there are total of 18 atoms in a unit cell, that is 8 at corners, 6 at faces and 4 atoms are inside the unit cell. Here effective number of atoms, that is n equal to 1 by 8 into 8 plus half into 6 plus 4 equal to 8 atoms. The radius of the atoms, that is R, equal to A root 3 by 8. So after doing all the maths, we get the atomic packing factor as 34%, which is the lowest packing efficiency among the all 4 cubic system. So that's all for today. अगर आपके कोई डाउट्स हैं तो प्लीज़ कमेंट में मेंशन करना मत भूलिएगा, और अगर आपको ये वीडियो अच्छा लगा हो तो प्लीज़ लाइक, कमेंट और सब्सक्राइब जरूर करिएगा।